So, what the line spectrum helps scientists figure out is that these lines represent very specific energies that electrons in an atom can have. And this energy is what they call quantized. It can only have values restricted to whole number multiples of a specific base value. So quantum, we need the smallest discrete quantity of energy. So we know that matter has small discrete quantities, we call them atoms, but before this, scientists hadn't really thought of energy being made up of discrete quantities. So when we talk about a photon, that's a small kind of quantity of electromagnetic radiation. I like to think of a photon as basically an atom of electromagnetic radiation. So the energy of a photon is directly proportional to its frequency, and it's inversely proportional to its wavelength. And it can be calculated by this very simple formula, where h stands for a constant known as Planck's constant, 6.626.0755 times 10 to the negative 34th joules, which are energy units, times second. So the larger the frequency of a photon, such as gamma radiation, the higher its energy. And the shorter its wavelength, like gamma, the higher its energy as well. So the difference between these two equations, E equals h times nu, where E equals hc divided by lambda, is in the second equation, I have substituted the fact that nu is equal to the speed of light divided by lambda. So if you are given the frequency of a photon, you can calculate its energy using E equals h times nu, or if you're given the wavelength of a photon, you can calculate its energy by multiplying h by the speed of light and then dividing by its wavelength. And remember, the wavelength has to be in units of meters. So let's talk about quantized state. These are discrete energy levels, and in our everyday life, we could think of these as maybe steps. So in an atom, an electron can only have very specific energy levels. It can, just like we can only step on steps, we can't step in between a step. An electron cannot exist in between these energy levels. And this is opposed to the way that scientists thought about energy before, which was on a continuum, that you could have any energy that you wanted to, but electrons can only have very specific energy levels, and we saw that represented in the specific photons that were emitted in an emission spectrum, or the specific photons that were absorbed in an absorption spectrum. All right, so what sort of problems are you going to see with this? Well, you will just be asked to calculate the energy of a photon, and if you're given the frequency, as I said, just multiply that by Planck's constant. If you're given the wavelength, then you just divide that into Planck's constant multiplied by the speed of light. So, a practice problem. What is the energy of a photon of gamma radiation that has a wavelength of 0.34 picometers? So, we want energy. We're given a wavelength of 0.34 picometers, so we know that the equation we're going to be using is energy of a photon is equal to Planck's constant times the speed of light divided by its wavelength. Now, the only thing is we've got to get this wavelength in units of meters. Now, all time must be in units of seconds, but usually that's not a problem. It's really the wavelength that is usually not given in meters. So we know that 1 picometer is equal to 1 times 10 to the minus 12th meter. So when I multiply 0.34 picometers by 1 times 10 to the minus 12th meter divided by 1 our picometers cancel out, and I end up with a wavelength of 3.4 times 10 to the minus 13 meter. So now I'm ready to plug into this equation. The energy of the photon is equal to 6.626 times 10 to the negative 34 joules times seconds, multiplied by the speed of light at 3 times 10 to the 8th meters per second, divided by the wavelength of 3.4 times 10 to the minus 13th meters. Now, before I even put these numbers into my calculator, I'm going to make sure that all my units cancel out. Seconds divided by seconds cancel out. Meter divided by meters cancel out. All my units except for joules cancel out, and that's an energy unit. So I'm going to go ahead and punch these numbers into my calculator, and when I do, this is the value that I get, 5.8467 times 10 to the negative 13th joules. Now, since I'm given 3 significant figures with my wavelength, no, I'm only given 2 significant figures with my wavelength. Sorry. I'm going to express my final answer with 2 significant figures. So my last allowable digit is the 8. I look to the right. My 4 is less than 5. So my 8 stays. And my final answer will be 5.8 times 10 to the negative 13th joule.